This video is about solving oblique triangles using the law of cosines. So we're going to continue where we were with the law of sines, but discuss more options. So let's denote these. We have now more options for oblique, I'll call them setups. Alright, so let's recall what we already know, which is we've talked about the case where you have angle, angle, side, and that gives you one possible triangle. We've talked about the case where you have angle, side, angle. That gives you also one triangle. And then we also talked about this third case, which is the ambiguous case, which is side, side, angle, which gives you 0, 1, or 2 triangles, depending on how they're set up. And all three of those cases all use the law of sines. And we've seen some examples of that already, perhaps not every single possible example, but we've seen a good flavor of what those can look like with the law of sines. So now we're going to add some options to it. The fourth option is that you could have side, side, side. Or in other words, you know three sides. Now this actually could give you 0 or 1 triangle, depending on what those sides are, as we'll see. And then fifthly, our last option, is that you could have side, angle, side, which also gives you only one triangle. Now, these new scenarios will not use the law of sines. The good news is you can't really mess it up if you try the law of sines, it's just that it won't work. So we need something else, and yes, it's called the law of cosines. The law of cosines is as follows. Let's go ahead and draw just a generic oblique triangle and label it accordingly. So let's put angle alpha across from side A, angle beta across from side B, and angle gamma across from side C. So a familiar setup by now, but if that's the case, here's what the law of cosines says. It says that c squared equals a squared plus b squared minus 2ab cosine of gamma. Now that seems a bit complicated, but just bear with me. There's actually a really easy way to memorize these since they're all so similar. The next one, we have an option for each letter that we have here for the side. So c squared is that. The next one would be b squared, would be a squared plus c squared minus 2ac cosine of beta. Okay, are you picking up the pattern now? So if you can't tell, the letter that's on the outside, in this case b, matches the angle letter for the cosine, beta, and then the other two letters inside to the right of the equation are just whatever were not out front. So if b is here, a and c is here. If c was here originally in the first one, then b and a were out there. Again, notice in the first one, c matches gamma. So there's a lot that lines up here. Can you imagine or guess what the third equation would be then? Well, notice outside front we haven't used a yet, so we'll use it. A squared equals, and then we'll use the other two letters, so that would have to be b squared plus c squared. It's always a minus 2 times those same letters, so bc, and then it's always cosine of whatever matches the letter on the very outside here of the side. So a here, which means alpha here. So these three equations are all the law of cosines. Yes, you do need to remember them, but as you can hopefully tell, there's a lot of similarity with them and patterns that make it easy to do. Let's take a look at an example where we want to, once again, solve the triangle. And we're given some information, namely that A is 15, B is 24, and C is 11. Now, notice there are no angles given in that information. That's fine, because we now have a case that fits that. So let's just draw a generic oblique triangle here and label the sides accordingly. It doesn't really matter which side you label what. I like to call the bottom B, so I'll say B is 24 here at the bottom. I'll put side A on the left side up here as 15, and I'll put side C over here on the right side as 11. So obviously this is a case of side, side, side. We know all three sides of the triangle. Now, There's a possibility, if you look back at the note for side, 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 that you could have 0 or 1 triangles with this case. So how do we know which it is? Well, there's a very simple test. All you have to check is the following. The two smaller sides must add to more than the third side. That's your simple test you can do to determine if you have 0 triangles or 1 for side, side, side. So take a look at our example here. The two smaller side lengths, of course, are 15 and 11. Add those up, you get 26, which is more than the other side of 24. So indeed, we're going to have 1 triangle for this case. Now let's just say you thought you wanted to try the law of sines for this particular example. Well, you won't get very far because notice you do not have any angles, and the law of sines, if you look at it, depends on knowing at least 1 angle, if not more. So we don't have any angles, which means law of sines goes nowhere. Well, if you're left with the law of cosines, it doesn't matter which angle you're trying to find first. Remember, we want all 3, but let's label them accordingly. Across from C we have gamma, across from A we have alpha, and across from B we have beta. Doesn't matter which one you want, I'll start with A for alpha. Okay, so the law says that the side across from alpha, which is A, I'm going to square. So I'll say A squared equals B squared plus C squared minus 2 times those same letters, BC, times the cosine of the angle that matches our letter out here, which is alpha. Alright, well, I should be able to substitute what I do know in for the letters and hopefully be able to find alpha out of this. So I know A is 15, so 15 squared equals, B is 24, so 24 squared plus 11 squared minus 2 times 24 times 11, just plugging numbers in their spots in its formula, times the cosine of alpha, which we don't know yet. We'll leave it there. So there's a lot of calculator number crunching here. Let's go ahead and do some. 15 squared is 225. 24 squared is 576. 11 squared is 121. And then 2 times 24 times 11 is 528. So I'll put that in place. So ultimately we want to solve for alpha here. Let's keep going with this arithmetic. If I bring these constants to the left side, I'll get a negative 472 over there equals a negative 528 cosine of alpha. Now we'll divide by negative 528 to get that the cosine of alpha is 59 over 66. Yeah, that's me leaving the fraction of 472 divided by 528 in reduced form. We want to keep this as an exact answer, of course, especially until the end. So I want now to get alpha, and we're going to have to just rely on our inverse trig functions to get it, right? To get rid of this cosine here, you can't just divide by cos. That doesn't mean anything. You have to use the inverse function. If I use that, I'll end up with alpha equals the cosine inverse of 59 over 66. Alright, so rounding this to the nearest tenth, as is our convention for angles, we should end up with 26.6 degrees for angle alpha. Now that we know alpha, we need to find one other angle, and as soon as we find either gamma or beta, we can just use the fact that these all must add to 180 and find the third one. So we have one more law of cosines to do depending on which angle we pick. Let's just pick beta this time. So I'm going to restart the law of cosines. Over here, and I'll make it b squared equals a squared plus c squared minus 2ac cosine of beta. But now we'll plug our numbers in accordingly. So b we have as 24, so 24 squared equals a squared, which is 15 squared, plus c squared, which is 11 squared, minus 2 times a, which is 15 times c, which is 11, times the cosine of beta. All right, so just like before, all we want to do now is first of all get the cosine of beta alone. So I'm going to skip a few steps there and let you calculate that all. But you should end up with the cosine beta equal to negative 23 over 33. Now remember, that's an exact answer, a reduced fraction. Don't turn that into a decimal yet. We want to make sure we only round our final answer here. To get rid of cosine, and therefore get beta alone, I'll just use the cosine inverse. So the cosine inverse of both sides would end up with beta equals the cosine inverse of negative 23 over 33. And rounded to a tenth, that should be 134.2 degrees. Alright, so now we know alpha and beta. That means gamma can be found simply by subtracting these other two angles from 180. And so if you do that, it turns out gamma should be about 19.2 degrees. And that's just using the rounded angle final answers here for alpha and beta to do the subtracting, and then give us gamma. Alright, well, all we had to do was find all three angles, and that's exactly what we have. Let's take a look at an application problem now, which reads as follows. Two aircraft carriers, which are large ships, okay, so two aircraft carriers, one cruising at 25 knots and the other at 20 knots, left the same base at the same time. 3 hours later, they were 100 nautical miles apart. What was the measure of the angle between their courses? Of course, a picture is going to be necessary here, so let's go ahead and draw one. We know that both ships left from the same port, so I'll make a dot for the port. One of them takes off, let's say this way, the other one takes off going this way. And we know that one of them is going a little faster than the other. We would expect that one to travel a little further, which is why I've purposely drawn my arrows slightly different lengths to convey that. So this one that goes a little further, that would be the one that's at 25 knots. And the one that's not quite as far is the one that's going 20 knots. Alright, but then it gives us a little key at the end here. It says 1 knot is 1 nautical mile per hour. So we'll have to use that to somehow get an answer out of this. Now, what we also know is that 3 hours later they were 100 nautical miles apart. So if they kind of just pause where they are here, 3 hours later, the distance between them, which I'll just draw as a dashed line, we know that is 100 nautical miles, or NMI you could use for nautical miles. Now we have to be a little careful here. Notice the units mismatch on my diagram. Right? These 25 and 20 numbers, those were given in terms of knots, which is a speed, or a speed metric on water. But then this other number down here, the 100, that's given as nautical miles, which is a distance. So we better be careful that we're not combining different units of measure, otherwise the answer is not going to come out correctly. We're going to have to convert them all to the same, but we can, since they said that these positions of the ships were taken 3 hours after they left. So if you multiply their speed by 3 hours, the distance of the 25 knot rate ship should be its speed times 3 hours, since 1 knot is 1 nautical mile per hour. So 3 hours would give us 75 nautical miles for that journey, and similarly 3 hours would be 60 nautical miles for the other. And then of course we want to know the angle between their courses, which we could call here anything you want. I'll just call it alpha. Alright, well now take a look at what we know. We know 3 sides of the triangle. It's probably not a right triangle, but we wouldn't even know if it was. And anytime you have a case of side, 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 that's the 3-side known case, we're going to have to try to use the law of cosine. Now, as you might recall, this case still might produce either 0 or 1 triangles, and so we have to do the double check to make sure that the 2 smaller sides add to something larger than the third, but it's not too hard to tell. 60 plus 75 is certainly more than 100. So we definitely have 1 triangle, and we definitely should use the law of cosines to find alpha. Let's go ahead and get that going. Of course, across from alpha, we'll call this side A, and the other 2 sides are B and C. It doesn't matter which one we call as which. But let's just go ahead and set it up with what we know for sure now, which is that according to the law of cosines, we can say a squared equals b squared plus c squared minus 2bc times the cosine of alpha. If we plug our numbers into it, we'll end up with 100 squared equals, it doesn't matter which number you use for b and c, we'll just pick some. So one of their measures was 60, so 60 squared, plus the other one was 75, so 75 squared, minus 2 times 60 times 75 cosine of alpha. There's a lot of number crunching here, so I'm going to skip a step or two and get down to where we could say that cosine of alpha, if you were to get that alone, would be equal to 100 squared minus 75 squared minus 60 squared all over negative 9,000. Okay, that's just doing the simple algebra to get cosine of alpha alone. We can then solve for alpha by taking a cosine inverse of both sides. So alpha will become equal to cosine inverse of basically this huge fraction, so I'll rewrite it as 100 squared minus 75 squared minus 60 squared all over negative 9,000. Now, it's quite possible to make mistakes in the calculator when typing all this stuff in, so just be careful, go slow. You should end up, try it out here, you should end up with an alpha measure of 94.9 degrees. Now, if you don't get that, double check that you're actually in degree mode, which it should be in, and then maybe go back through and retype things to make sure you didn't accidentally miss a square or a negative sign. But alpha being 94.9 would be the angle between the courses of these ships.